The next type of application problem are going to be problems involving uniform motion. Uniform motion just means that we're traveling at a constant rate. We're not speeding up and slowing down, speeding up and slowing down. So this rate number will be the same. We need to know the formula from physics to calculate uniform motion problems, that the distance traveled is equal to the rate or speed traveled times the time. Here's an example. Two planes leave from Atlanta, Georgia. One makes a 5.2-hour flight to Seattle, Washington, and the other makes a 2.5-hour flight to Boston. Those are the times of each of those flights. It says the plane to Boston averages 44 miles per hour slower than the plane to Seattle. That sentence compares the rates. It says that the total distance traveled by both planes is 3,124 miles. Determine the average speed of each plane. For uniform motion problems, I find it helpful to make a chart, to make a table, and organize the information from our problem inside this table. Along the first column of the table, we will just label each of the quantities: distance, rate, and time. Now, for the second row and the third row, we're going to discuss each of the two traveling parties. We have a train, we have a plane that's going to Seattle. So let me label that. And then we also have another plane that makes a 2.5-hour flight to Boston. So this other plane is going to Boston. Now, we want to get as many of these cells figured out as we can. We do know the time of each of these planes. The time of the one going to Seattle is 5.2 hours, and the one going to Boston is 2.5 hours. Okay, it says the plane to Boston averages 44 miles per hour slower than the plane to Seattle. And then we have a thing that says the total distance traveled is 3,124. It says determine the average speed of each plane. Okay, so if we're looking for average speed of each plane, we're going to let x be equal to the speed, or also known as the rate of, and let's just let it either be to Seattle or to Boston. Okay, so I say I'm going to let x be equal to the rate of the plane that's going to Seattle. Okay, so that's going to be x right in there. Now, for the plane going to Boston, we know that it is 44 miles per hour slower. So if we think of these two planes, and I say that the rate of the plane to Seattle is equal to the rate of the plane to Boston, that is not true. What we need to do is make those balance out so that it would be true. Okay? Now, the plane to Boston is 44 miles per hour slower, and so the plane that's going to Boston, the one that's going to Seattle is, let's see, what did it say? The plane to Boston is slower. This one's slower, so to make those equal, we will add 44 to both sides. So this is a way to make a true statement up here. Now we have assigned the rate of the Seattle plane a value of x. That's going to be equal to the rate of the Boston plane plus 44. And so if we're looking for what quantity to put inside the rate of the Boston cell, which is right in here, The rate of the Boston plane is going to be x minus 44. It's the rate of the Seattle plane less the 44 miles per hour that it is going slower. Now, in a uniform motion problem, once you get 2 of the 3 columns filled out, what we're going to do is write that third column as a function of the other 2, using our formula distance equals rate times time. So we can say that the distance of the Seattle plane can be expressed as the rate of the Seattle plane times the time of the Seattle plane. So the distance is represented by 5.2 times x. That's the distance that it has traveled. We'll deal with this 3,124 in just a minute, but this is the distance of the Seattle plane. The distance of the Boston plane is this quantity of the rate of the Boston plane times the time of the Boston plane, and that is 2.5 times the quantity x minus 44. That's the distance that the Boston plane has traveled. Now, once we get, like I said, 2 of these 3 columns figured out, we're then going to use that third column, because there's our unknowns in x, to write the model for our word problem. Now, there should be something up here in our word problem that tells us how the distances were related. And this last sentence says, the total distance traveled by both planes is 3,124 miles. So this is a true statement when we say that the distance of the Seattle plane added to the distance of the Boston plane is 3,124. We do have expressions for the distance of the Seattle plane and the distance of the Boston plane. So that I have room, I'm going to come right up here. So the distance of the Seattle plane is, from that cell, 5.2 times x. The distance of the Boston plane is in the box here. It is 2.5 times the quantity x minus 44. And those 2 distances add up to be 3,124 miles. There's our model. And let's just use a little bit of algebra to solve it. So first of all, clearing grouping symbols on the left-hand side, we have 5.2x plus 2.5x minus 2.5 times 44 is 110. We'll combine like terms on the left-hand side and go ahead and add the number 110 to both sides. So once we simplify, we will have 7.7x on the left-hand side. On the right-hand side, 3,234. Solving for x, divide both sides by 7.7. And so x, which once again is the rate of the Seattle plane, is going to be 3,234 divided by 7.7. We will get 420. Now, the correct label on that is going to be in miles per hour. Okay, and this is the rate of the Seattle plane. It said find the speed of each plane. Well, the rate of the Seattle plane is 420 miles per hour. The rate of the plane going to Boston was 44 miles per hour slower. And so when we take 420 minus 44, That gives us that the rate of the plane to Boston is 376. Rate to or of the plane going to Boston.